Hi everyone, I'm Natalia Petridou. I've been talking through the day. So I'm from the high field group of the UMC Utrecht in the Netherlands. So I'll briefly say a couple of things about grain and neck and spineco. I think I can be quite brief actually because you've heard most of the concepts already. So it's all about specificity to the capillary bed. And we know we're looking at the vasculature in a very small part of the brain over there. It's a corrosion cast, so you can actually see the vessels, capillary bed, intracortical vessels draining or supplying blood to the capillary bed and draining veins. So the quest is to be as specific as we can to the capillary bed because it directly interfaces with the neuronal tissue. And so I am talking about bold, actually. And what is our contrast at a high field or higher field? It's coming from extravascular effects. So all the bold signal that we have is from outside the vessels. We don't really get intravascular signal at high fields at all, or very little. So what is that signal that we have? It's two kinds basically. I think you may know this already. We have a static dephasing regime around larger vessels, which is our T2 star effect. What does this mean? If you have water molecules or spins, they move around in a field that's larger than their path. So this is a larger vessel here, an illustration of, you can also see it on the graph on the right. So this is a static dephasing regime. And if you apply a 180 pulse, Spinnaco pulse basically, you can reverse the dephasing that's caused by this situation. Around small vessels, we're in the dynamic dephasing regime, which is illustrated here. This is a T2 like effect. So the field that the spins experience where walking around is actually variable. So when you apply 180 pulse, you cannot actually refocus these effects. So this is the two contrasts basically that we have for grain and echo and spin echo. You all know this, grain and echo and spin echo, the refocusing pulse. And so basically our grain and echo is T2 star weighted, signal contribution from all the vessels, relatively low specificity to the capillary bed, although we do get signals from the capillary bed, and very high sensitivity. Spin echo data is more T2 weighted. Like I said, the signal from the larger vasculature is minimized. It's very specific to the capillary bed, but it has a couple of disadvantages. That's why it's not commonly used. One key one is that it has a very low sensitivity, so the percent bold signal change that you get intuitively is much smaller because you are looking at much less of the vessels that are in there. And also it can be a little bit SAR demanding as well. And the combination of these two make it much more difficult to actually do a true sub-millimeter resolution experiment. And on the right there, the graph that I'm showing is actually from it's quite old work from Boxerman that shows the sensitivity between, maybe I'm supposed to point like that in the air, maybe I can do this. The sensitivity of spin echo that's closer to the capillary, while grain and echo is in essence sensitive to all the vessels. But yeah, spin echo is actually quite difficult to make it work even at high field. But some examples, one is from here, it's a very famous one from ESA's work, where they use, I'm using this as a comparison basically to give you an idea of what the maps may look like. It's trying to image ocular dominance columns, which is, I think you probably know, columns in V1 that respond to either one eye or the other. And this is a representation or a view that is a flat cortex basically for grain and echo and spin echo for one subject, 2 different days. And you can see you can obviously get a map from both sequences, but the spin echo may be a little bit more specific. It's always a little bit hard to truly evaluate this with ground truth because we know those are there and we know from histology, but we cannot really see them otherwise. So at the end of the day, I mean, okay, we know this should work better, but how bad is that? It's hard to tell. Then the other example I'm showing on the right is a topography example. Again, we have our grain and echo and our spin echo. I mean, they both pick up the same pattern, but I think in this example that I'm showing is that the noise in the spin echo is a little bit more evident. So you can see the maps here a little bit more granulated as compared to the grain and echo that shows this topography quite nicely. So it also goes back to what Renzo was saying. At the end of the day, what do you use? It depends on your question. So it would be ideal to have a sub-millimeter isotropic spin echo, but it's a little bit tough. You may need to scan for a very, very, very long time and suffer all sorts of other problems. I added this earlier and I forgot I had it. Again, it's work from here. The data that I showed a moment ago. From this data, the more recent work is try to compare the point spread function of the grain and echo as compared to the spin echo. So at least you can have a quantitative idea of the spatial specificity between the two as compared to an anatomical feature that we know should be there. And this is the result. So it's expressed in terms of full width at half maximum. So spin echo would be here, grain and echo would be there. If they were identical in their point spread function, which is a spatial spread, basically, that's what the point spread function is telling us. And the distribution of all these points would be on this line, but it isn't quite. It's one subject and another subject. So the grain and echo is always a little bit larger as anticipated, because of course it includes the larger vessels that make the activity a little bit more blurred. Roughly, in this, on average between those two examples, it's the spin echo is about 0.8 millimeters and the grain and echo was about 1 millimeter in spread, just to give you an idea. And a little bit about the dynamics of the two kinds of scans. So this is a cortical depth analysis that we did some time ago. Again, we have our vascular compartments now. They're broken up into cortical depths, or layers, if you will. Pile surface, and then at 1, 2, and 2 to 3 millimeters cortical depth. And we extracted curves from these compartments. Of course, this is an illustration that you see on the right. This was a very short stimulus, visual cortex, and TR was actually quite fast in that case. I think it was around 800 milliseconds, if I remember correctly. So we can get a very good estimate of our hemodynamic responses. The pile surface, you can see the amplitude of the curve is really high. It's very delayed, it's very wide. All those features reflect the fact that there's blood that starts from here, flows up, pools, and it goes to the pile surface later. And then as you go deeper and deeper, you can actually see the features between the two contrasts. The spin echo is the smallest curve in the purple. So that's let's say it's only microvessels. It starts very quickly, not a very high amplitude, as I mentioned before, and it and it decays at some point. And then green, red, and black are the grain and echo curves from here, here, and here. So deeper in the cortex, if you look at the early part of the curves, the grain and echo and the spin echo is about the same. So they're both heavily weighted towards the microvasculature, but from the time to peak and onward, you start seeing the effect of the blood pooling in the grain and echo. So your specificity starts to go down over time. And we can look at it in a graph like this. So it's a ratio of, in essence, grain and echo over spin echo. Now it's expressed in terms of R2 star over R2. So they're about the same. Now looking here, this part, they're about the same until the time to peak of the spin echo, and then whoop, microvessels or larger vessels kick in. So if we're fast enough, we could actually be quite specific with grain and echo as well. But that's not really realistic if you do a true laminar experiment. So bottom line, that's it. So what do? Depends how much, depends on your hardware, depends on a lot of things, on your question. But this is a summary between the two kinds of contrasts. So in the end, we end up with crane and echo more often because it's actually more feasible to do, especially for very high resolutions. And now very quickly I want to mention about grace, which I don't use. I'm not really an expert to really say anything super intelligent about it, but it is a technique that combines the advantages of both, crane and echo and spin echo. So you have, it's a 3D volume acquisition. You can see the case space of an illustration of the case space here. So you start your excitation normally, and then it's followed by multiple refocusing pulses through your readout, and after each refocusing pulse, you acquire a K plane, and you move in the volume. So you have a combination between both T2 weighting and T2 star weighting. So you get a little bit of both. Basically, you improve your specificity a little bit while maintaining some sensitivity as well. But of course, because it's a 3D volume acquisition, you need to use parallel imaging to actually speed it up. There's some examples from Grace. This is from Ben Poser. It's a whole brain Grace acquisition. I think it's not too recent, but it's from a nice MRM presentation. Then this is an example from Feinberg, who actually first developed the method, and more recent work by Maastricht, Valentin Kemper, just to give you an idea of what the data may look like. Some discussions in the community that relate to some blurring that may be included in this technique. But again, I'm actually quoting from people that are experts in this technique that it may not be as bad, especially when you compare it with other ways to do a true spin echo acquisition. But at the end of the day, yes, indeed, the sensitivity is lower than crane and echo, so we're back to square one. That's it. Any questions?
So there's a perspective from which we sort of started it there. So you had a question?
I had a question.